All right. So I don't quite have your exams done yet, but I made some good progress. So I'm hoping to have them back for you on Thursday. So chances are good that I'll pass back the exams Thursday, and we'll go through the solutions, kind of address any questions or issues. So you'll probably have an indication if I end up posting exam grades to Moodle before class, probably the night before. That probably means I've got them ready to pass back. So if not, we'll start on disinfection on Thursday, but probably we'll go over the exams, and then disinfection we'll start that a week from today. All right. We left off before the break talking about membranes. So we're going to pick up there today. Probably post your next homework assignment sometime next week, maybe later in this week. But I think we've got a bit of time on that. And it'll cover the two different kinds of filtration plus the disinfection. So got a bit of material to cover before we really dive into that anyway. Okay, so we left off with this problem last time. I kind of suggested that you take a look, it might be a good or convenient way to practice to just change this number up here. Say, okay, well, what happens if I change that to 20% or 100%? What does that look like? So, but we solved that last time. So what I want to move on to today is really getting into a bit more about what's really happening at that membrane surface, and how does it matter? Why does it matter when it gets dirty? And to give you a few more formulae to deal with membrane systems in terms of that mass and solute balance. So first, I want to take a look at membrane operation from a water perspective, or whatever, a solute perspective. So whatever it is that we're trying to remove, whether that's salt from like reverse osmosis, or if it's particulate matter or something like that. So considering the stuff that we're trying to remove, we can define that much like we have with like C over C naught kind of stuff by saying, let's define a fraction rejected. And we'll say some capital R here. I'm trying to keep my nomenclature pretty consistent to the different pieces where I've taken this material from. Membranes in particular, there's very little material in our actual textbook. So I've drawn this from some other places. You can find those in the recommended reading spots. They should be free through LSU libraries as ebooks. Let me know if you need more direction on where to find more about membranes, but that's the deal. And I'm just trying to keep consistent here. So we have a few different R's. The capital R we'll say is the fraction rejected. So it's the portion of particles or whatever rejected by the membrane. In that example we talked about, that'd be the portion of these algae rejected. So in this case, R is going to be, has a fraction rejected, should be 0.9. And we could define that as we see here, 1 minus the amount that goes through divided by the amount that we're meeting the membrane. So we could, just while I'm at it, we'll say this is 1 minus the concentration that permeates divided by the concentration in that feed. So if we're rejecting 90%, then the portion that's making it through is 10% or 0.1, right? So this would be 1 minus 0.1 equals 0.9. So just a quick look at how that would play about. Okay, so that's really all we're saying. It's pretty simple, straightforward in that manner. We'll take Cp as the concentration that permeates, Cf's concentration in the feed. You could use milligrams per liters or some other unit here. Those are just examples. Now, if we want to express that, but we realize, well, we're rejecting 99.999% of stuff, you'll eventually lose track of how many nines, right? Where did that decimal place go? And how do we express that more easily? Well, that's when we come to our log terminology. And in this case, we can say R log is just going to be the log of CF divided by CP. Now this, you'll see, is inverted. That's just a way to arrange it in a manner where we can say, oh, we have a 3 log removal, meaning that, you know, this what's remaining in the feed compared to what's in the permeate is reduced by that number of logs. So if we take that algae problem and instead of doing the 1 log, which is 90%, so 1 log removal, that's 90%. In this case, we say 99.99%, and we want to know how to express that with log. Well, if we take just the regular R, we would say 1 minus 1 over 10,000 is equal to 0.9999, or we can write that as 99.99%, right? It gets a little bit repetitive and difficult just to say it. So instead, we could look at that and say, well, let's put it in the R log equation and say that's going to be, if we take the log of 10,000 divided by 1, so the log of 10,000, well, 10 to the 4th, remember that's how the logs work. Take 10 to the whatever's in the brackets equals, you know, the number on the right. So 10 to the, excuse me, I said that backwards, but 10 to this number is equal to that number, right? So 10 to the 4th is 10,000, meaning that we have 10,000 times the amount that is in the feed than it is permeating through. So it's 4 log rejection or 4 log removal. So that's pretty straightforward. Just wanted to highlight why it's showing up that way, why it looks like that. Very similar to what we already talked about in terms of just units in general and, you know, log reduction for like bacteria, for disinfection, things like that. So we've got the solute balance here with a capital R, and we could also take a look at membranes from a water balance, and here we're going to use the lowercase r for recovery. So when we talk about a membrane operation, one of the things that we recognize is the retentate stream, or the concentrate, is basically wastewater, unless that's like what we're trying to make, right? Orange juice from concentrate, you know, we're trying to concentrate it. But in general, if we're treating water, our point is to get rid of the stuff, and we're producing this flow rate. So we'll say this concentrate flow. This is going to wastewater. So this is water that we are not going to use in any way. And if we sent it back through the membrane, it's just going to bring all those particles and really junk it up even worse. So the whole point is to push these away somewhere else. We can treat them in some manner, whatever's appropriate. Maybe that involves membranes, maybe it doesn't. But the point is it's going away from the membrane, and that's can be a fair amount of water lost. So in the case of desalination, we might have to desalinate a bunch of water and make really, really salty brine for this wastewater, the concentrate, right? It has to go somewhere. And so what do we do with that, and how do we account for the water balance here? Well, we can describe it with this lowercase r as water recovery rate, simply meaning the flow in the permeate divided by the flow in the feed. And so if we know this water recovery rate, then we can know essentially where all the water is going if we were to draw a diagram, right? So if we draw a simple box diagram, say we have a membrane across, that means here's we'll say this is the QP, here's the QF, and of course some water is leaving as the Q retentate. So in this circumstance, we see that if we know the ratio between QP and QF, then we actually should be able to find the amount that leaves, or at least the portion that leaves if we needed to, because it can only go in 3 places, right? It's coming in and going out 2, going in one spot, going out 2. So that gives us a fair amount of information. So if we take that equation plus just our simple water balance equation, what's coming in is equal to what's going out, then we can know all the parts, right? And sometimes that'll just have to be something you intuitively do in order to find a concentration. You might have the water recovery rate and some sort of rejection percent. Putting these pieces together, you should be able to solve for the flows so that you can solve for the concentrations and do the mass balance one step at a time, right? Like do the water balance, then do the solute balance, and so on. Okay, so just a real quick example. If we have a membrane system treating 100 liters per minute of water, 15% of it goes to waste, then what is R equal? So essentially, what's left is 85%, right? So if 100 is coming to the membrane, and we'll draw it this way because I ran out of room, and then 15 is going to waste, then that leaves 85 here, right? We could talk about it in percentages. The example here just made it real easy, said 100, right? So we can just leave it like that. So 100 is coming in, 15 is going to waste, 85 is going through. So it really simply becomes 85 over 100 is 0.85. Okay, so very straightforward. Your task then will be to, when we take a look at the equation sheet, I'll post a new one shortly for your next exam. But when you study this, you'll have this one. You have the solute balance, fraction rejected. You'll have these equations. Your task then will be to recognize when and where you use them, right? You don't need to use these formulas in some cases, but you ought to know what does that lowercase r stand for, so you know how to relate it to a problem, right? So that's probably the only difficult part here, is building your vocabulary in order to apply it. Okay, so then the other major term that we deal with would be the flux. We already talked about this concept in a way with the granular filtration. In granular filtration, we had the flux across the media bed in some sense. That was our loading rate. We're adding the water onto this media bed, and it's going through some surface area, and so we get some flow rate divided by area that we could also call a flux. So really what it is, whatever units we use could be cubic meters per square meter per second, could be liters per square meter per hour. Whatever it is, it ultimately can come down to a speed at which water is traveling through some surface, right? Some porous surface. So we'll describe flux as J, and say J is going to be, like as a rule, this is the flow rate per area, right? So we always know if we have the area and a flow rate, we can solve for flux. We'll have other definitions or equations to define flux and some other terms as well. But overall, this is the meaning, is the flow rate through an area. Okay. Now, one thing to note here is this is flow through that area, right? So that means that's going to be the QP. So we might be tempted, if we have some sort of membrane, got water flowing through it, this would be our Q feed. Now some of it goes away as the concentrate or retentate, and then some of it's going through. So you might be tempted to think, oh, we're feeding the membrane 100 liters per hour, so that must be the Q here. Well, actually, when we are talking about flux, it's the amount of water crossing that plane. So we have to take the Q P here, not the QF, right? So it's important that we're using the flux across the membrane. Okay. So still relatively straightforward there. Membranes in general, for the most part, it's a nice, simple, no reactions involved, so it kind of keeps the the mass and water balance is relatively simple. Okay, so let's take a look at a problem here. I'll give you a few minutes to work it and see if you can apply these, apply this knowledge so far to this. I'll read it and then I'll let you work on it. So it says a Dow FilmTech SFX 2860 membrane module contains 5,760 fibers. The fibers are 1.87 meters long with an outside diameter of 1.3 millimeters and an inside diameter of 0.7 millimeters. And it asks us to calculate the water production from one module if the flux is 75 liters per square meter per hour, and the flow direction is either 1, outside to in, or, and 2, inside to out, and then compare the answers. So we'll have a system here. I recommend drawing the system first, so you have some idea of what you're looking at, what you're thinking about. So I'll give you a few minutes and then I'll start drawing up and piecing some of the pieces together. Real quick, just remember the flux, Q, P over the area. All right, so take a few minutes to work on that. You guys only work together when I'm not here? What's up with that? Point is to learn, so please feel free to be working together. Even anybody online, you're welcome to talk, through the chat with one another if you want. All right, so I've done the first part here for you. Hopefully you can kind of see what I'm doing. I drew up kind of a sketch of one of the fibers. This is a module with a whole bunch of small fibers, so if you wanted to draw it, you know, you just like put a whole bunch of dots, I suppose, and each of these are a fiber going through, and this is one long module system, right? So I just drew one fiber here and just remembered to say, all right, well, we have, you know, almost 6,000 of them in one module, so we have to account for that. So we solve for the area for the one fiber, and first we do it with the outside diameter as a separation layer, because we're operating outside to in. That means the outer surface area is what's important. And so we took the 1.3 millimeters, that would be 0.0013 meters. Our surface area for the fiber, so need a little bit of geometry here, should be the circumference times the length, right? That would be the surface area of a cylinder. And so I took the circumference by saying 2 pi r, or just diameter times pi, times that length. So that gave us 0.00764 square meters per fiber, and multiply that by the number of fibers we had in the module. That gives us about 44 square meters of membrane area in one module. So that kind of gives us the scope of what area do we have. Now we can compare that to the flux we were provided. So the flux value here is kind of unique to a given membrane and operation condition. So given some membrane, given some pressure and water parameters, it achieves some kind of a flux. Depends on how resistant the membrane is to the flow. We'll see that in a minute. Basically, we have some default flux that we can achieve, and so then the question is, how much membrane do we need to achieve our goals given that situation? Or in this case, the question asks us for the water production. So that means kind of like a flow rate, how much water is produced presumably over time. So, because you know they could specify in 2 hours or something, and then it's a volume. But without that, we kind of assume it's a production rate. So we're going to solve for Q, and really that would be QP, right? And we could say, well, we just rearrange the flux equation to say our flow rate's going to be the flux times the area. And if we take a look at the units, the flux was already in per square meters, conveniently, and we solved it in square meters. So we can even just leave the liters alone because those don't get involved, because the square meters will just cancel. So we have 44 square meters times 75 liters per square meter per hour gives us 3,300 liters per hour, essentially, right? 3299. So that would be the outside in, and to do the inside out will be very similar. I'm just going to spend a moment. I've got an Excel sheet. I was just doing it over here. So it'll just take me a moment. I'll write it up. Feel free to check your answers and predict. When we compare them, you could say one is some portion of the other. This one's three times bigger or whatever. It just told you to compare them. So whichever way you feel is useful would be a fine way to do so. Okay, so I'm just going to take a moment and write this up for us as I work. Okay, so if we take a look, really the surface area should be directly proportional to the flow rate. So we could have just compared the surface area, but if we take the flow rate from 2, which was 1776, divided by the flow rate for 1, which is 3,300, should be about 0.54. So we're getting a little over 50% of the water that we would have by operating inside compared to operating from the outside. As the separation layer. So that small little change made a big impact on our surface area across all these fibers. That's kind of the point. Okay, does that make sense? Any issues? All right, so we didn't really deal with water recovery stuff, but just kind of a membrane problem to get us going. We've got a few others we can look at as well. All right, so another topic I hinted at earlier is what kind of pressure is required to actually push the water through the membranes. And so when we take a look at a given membrane, we're saying we have to achieve some specific flux that we might want or you would expect to have for a given membrane. And we'll call this pressure that we're going to apply transmembrane pressure. So pressure that's like we have some high pressure above the membrane, a lower pressure below the membrane or across the membrane. That differential is going to be that kind of a pressure gradient driving water across. And so we'll define that as the pressure in the feed minus the pressure in the permeate. Now we can get the membrane researchers can get pretty high tech about, okay, where exactly do we measure the membrane pressure? Can we measure it like right inside the membrane itself and all that? But for our purposes, we're just looking at if we pressurize a feed and we're comparing that to what happens, to the pressure drop across that membrane, where we have some pressure in the permeate different than the pressure in the feed. Now, you can actually sequence membranes and set up a whole bunch of membranes. So you could take this and go to another membrane, and so on, and really just pressurize it really heavily up here in the initial feed. You'll have some pressure drop, and it'll be like a waterfall, right? You're dropping a bit each time. So just to kind of give you a sense of how the pressurization systems might work, is you're just looking at that drop across it, and you expect some drop. It doesn't have to be all the way from 100 to 0. In fact, the little picture example we saw water kind of spraying out the other end through the permeate. It looked like it had pretty good force or pressure still. We could just ramp up the pressure a whole bunch, and then you have a lot of pressure coming out because it was only so much of a pressure drop. So that's just to say it's that difference there, the pressure in the feed compared to the pressure in the permeate. And we'll talk about these in pascals. Okay, so again, that brings us to kilograms, meters, and seconds in terms of the units. And we don't even have to worry too much about the conversions because we have an equation that will kind of handle that for us. So our equation then for how the pressure affects the flux will be the flux is equal to the transmembrane pressure, so that pressure drop, divided by the dynamic viscosity of the liquid times some sort of innate membrane resistance value that we're going to measure in per meter units. Okay, so what we're talking about here, and if we take a look at the units here for the flux, we know it's going to be cubic meters per square meter per second. If you stop and look back about what a Pascal is, it's some newtons over some area. It should all come back to these units. We know that dynamic viscosity is kilograms per meters per second. This membrane resistance, you can think of it's a per meter unit. It's kind of like what portion of force is reduced across some meter. Now, we don't ever make a membrane that's a meter thick. They're actually very, very small, right? So it's a very, very small portion. So when we think about how much resistance across one meter of a membrane, that's going to be an enormous number compared to what happens in reality. We're just using meters to be consistent with all the other units. So when we take a look at membrane resistance values, it's actually typical to have something like 10 to the 11th per meter as a value. That's just kind of the way it is. But if we take from 1 meter and go down to like maybe a micrometer thick, then we say, oh, okay, there's some resistance across this thin area. Okay, so when we talk about these membranes, we've talked a lot about them, but we haven't actually taken a look at real pictures of them. So here's some electron micrographs and a drawing of what they might look like. And I want to show you this to kind of show you where the resistance is really coming from. And we'll talk a little more about membrane fouling and how that might affect the membrane resistance. So a given membrane is just going to have some resistance to flow. That's kind of the point, right? It's resisting the flow so that the particles can't get by. I mean, it'd be nice if the water could magically sift through with no resistance, but that's not reality. And by the way, if you imagine trying to filter honey, very viscous, you can imagine that's not going to go so well, right? That's what we're seeing right here with the viscosity. If the viscosity is high, then you have to have a lot of pressure to counteract that and get the same flux, right? So the fact that the viscosity of water changes with temperature can actually be important as well, right? So high temperature water might actually get some benefit there. Okay, but mostly what we're looking at is the resistance here. And even just looking at these micrographs, we can see, for example, the separation layer of this part A here, is really this area. All of these larger pores, that's just support material. We need it to actually like put the thin layer on top of and kind of build a platform for it to sit on and withstand pressure, but we don't want it to resist any flow of water, as little as possible. So it's kind of like columns holding up a roof or something, right? So it's like your support structure there. We try to just let all the water through now that it has crossed the membrane. And so in this case, water would flow in this direction, assuming this top layer is the separation layer, and then should have no issues going elsewhere. So that means any fouling or particulates hopefully are removed and go away from that surface. Like that's kind of the idea. So we can take a look at each of these pictures and see, well, in this case, we can still see some pores. If you look closely, there's kind of some channels here, but they're really fine. And then again, we see this layer of support, right? So you can see the design here as we try to get a really, really thin layer that's providing the high resistance, also the high separation, but we really want to make that separation layer, that resistant part, really small. Okay, a couple more examples. Even this one down here, you see is really smooth, flat surface, really, really thin. You can't even really see pores in it, but you can imagine water might be able to squeeze through the cracks, right? So maybe these ones on the left are more like a microfiltration, ultrafiltration, and here we might be getting down to sort of nanofiltration. So you can see how that's going to resist the flow of water, and that's sort of what it really looks like. Now, as we start talking about fouling in a moment, this little graphic up here shows some sort of a membrane where water could go through, but as you stack these little particles on, you might form what we call this cake layer of particles that water has to filter through even to reach the membrane. So it's almost like you're adding a membrane on top of the membrane if you get too much fouling going. So we want to generally try to remove that, even though maybe it helps us remove more particles from the water. It's at a cost of how much pressure, the energy to apply that pressure. Okay, so let me elaborate a little further on this resistance. So the membrane resistance, or the total resistance, RT, which was from our equation, right? We said the flux was going to be equal to the transmembrane pressure divided by the total resistance, RT. And I do apologize for the one more R here today. But that total resistance times dynamic viscosity. What we're looking at is what goes into this total resistance. So what we just saw, you can tell this membrane is going to have a fair bit of resistance just by its nature. The clean membrane, it's manufactured that way, there's going to be some resistance, right? That's by design, that's just the way of it. So the membrane itself is going to have some resistance. The total resistance is going to be the sum of a few different components, right? That'll be just simply the fact that it's a membrane. Then we'll have some resistant due to fouling, and then potentially resistant due to a cake layer formation. So I'm going to draw a little sketch. Let's assume that we have a very small pore separation layer right here. So there's small pores that water can make its way through, and then sort of larger channels for water to come out of on the other end. So something like that. So in this case, especially at this fine surface, that's really what's providing most of the resistance due to the membrane itself. Then we can have foulants that are added to it, and I'm going to put those in a portion of this. So as these little green particles come into play, they'll start sticking inside the pores and around, a few on top, and we'll just have some general fouling that kind of shrinks the the pores by these particles just kind of sticking to them and kind of hanging out there. So here would be resistance due to the general fouling. And then lastly, we would have a cake layer forming, and I'm just going to draw it a little lower so just distinguish it. These would all happen kind of all over, but I'm just going to draw it this way. So after you get some of that on there, we already mentioned this layer, this fouling layer would become, would start blocking enough materials that you start just having an accumulation of physical layers on top of the membrane, so the water has to go through that. And so here's where we would say this is the resistance due to the cake layer. Now, very simply, it's whatever resistance is there is the total resistance, right? You just add them up. So we might do a problem or something that says like, well, here's a scenario. What happens if fouling now doubles your resistance? What happens to your pressure requirements or something like that? It's actually pretty straightforward. Mostly what I want you to recognize is how this works and therefore why it's important to clean our membranes. And so in real operation, we will tend to clean the membranes quite frequently. So for example, there's an application called membrane bioreactors for wastewater treatment, and you'll actually stop the membranes just really briefly. It's an automated system, and backwash for like a second, just like pulse a little bit of water backwards through them, like every minute or something. Or you'll apply some vibrational shaking every couple minutes. So there's these techniques you can use just to try to get the fouling layer off as much as you can. And then perhaps, in that particular scenario, then they would take these and chemically clean them every like 5 to 6 months. So they'd give it a chemical cleaning to get all this stuff away, but they would be shaking it and doing these other things to try to really keep any cake layer from forming and clogging up stuff. All of that type of thing will depend a bit on how exactly the membrane is designed, what it's actually operating, but typically the backwashing kind of stuff happens with a lot more frequency than the granular media filters that you have to drain and backwash like we saw. Okay, one last definition for us that's very related to this stuff is the permeability. In fact, we are saying that a term, LP, for permeability is the flux over the transmembrane pressure. So it's kind of like how likely is it for water to make its way through? And we just saw that flux is equal to transmembrane pressure divided by RT times mu. So if we rearrange this a little bit, we could realize that LP is just 1 over RT times mu. So they're just kind of related there. It's another way to describe what's going on. You'll probably see permeability as a concept in groundwater flow, as you want to understand where groundwater is going. We deal a lot with Darcy's law, permeability kind of stuff. So definitely relevant there. It's a similar concept here, kind of like how porous is it, or how, what are the pathways look like for water to flow. And we also have on this slide a couple other pictures just depicting really how the fouling can work. We might have complete blocking where a particle just really sits and plugs the pore directly. That's not quite as common. We would try to operate with a situation where the particles we're trying to remove are a little bit too big for that or a little too small for that. Standard blocking is maybe the most common or standard conception, where it's just kind of lining the walls and therefore shrinking the stuff. Intermediate is just a step where we're starting to get a cake formation layer across, but it's not really there. And then finally the cake filtration, which, in this scenario, we would imagine there would also be some of the other kind of standard blocking, but the point is we've established that cake where water has to flow through it in order to make its way through. Okay, make sense? All right, so that's about it for the technical aspects of membranes that I wanted to cover. So now we know about the water balance, the solute balance. We understand how the pressure is affecting membrane operation and how fouling is affecting that pressure. And so at this point, I just have some practice problems for you to look at. So we'll go through this one. I have used this one on an exam before in the past, so you can kind of maybe get an idea of what the types of things I might think about. So this one says operators of a small groundwater cleanup decide to implement cross-flow microfiltration membrane unit as a pretreatment to make sure that it doesn't contain any large particles that can clog the next treatment. The system must treat 200 liters per hour. It utilizes a membrane. So when it says it must treat that much, that's meaning we're probably producing that much, right? So that's a little bit vague, but I would say that we have to treat that amount. So QP, I would say, should be that 200 liters per hour. With a pore size of 2 micrometers, it must recover at least 95% of the water. The influent contains 30 milligrams per liter of particles, and the membrane rejects 85% of them. So first of all, A, label them. B, what is the concentration in the permeate? C, what is the concentration in the retentate? And D, if the membrane has a flux of 25 liters per square meter per hour, what total membrane area is required to meet the flow demands? All right, so take a couple minutes. Feel free to work with one another. I will solve this with you, and I think that'll be it for today. All right, so I went ahead and started a bit just on this page. I've got more room for us to work on things in the next. So I'll go through B real quick, and then we'll go forward to C, and I'll start working that up, C and D both. Let you finish wrapping up your attempt as well, or you could follow along. But real quick, part B, for concentration in the permeate. Well, we know that that's going to relate to our fraction rejected. We said 85% was rejected. And what you'll notice here is you can probably have some intuitive grasp of this, even if you forgot the formula exactly. But the formula is this R is 1 minus Cp over Cf. And we can say that that's 0.85 because we were saying 85% were rejected. So we are given the concentration in the feed at 30 milligrams per liter. So it's just basically 15% of that is 4.5 milligrams per liter. Okay, so then next is part D. It says if the, excuse me, it's part C. C and D here, okay. So I'm gonna start working on part C, and as you'll notice a moment ago, I started writing the mass balance that we'd need, which is what's coming in is what's going out, right? So take a few more minutes while I work this. All right. So we can see for part C, it's a little bit more involved. We need that overall balance of what's going in and out for the solutes. Means we have to find the flow rates, which means we have to get that water recovery rate, which is 0.95, equate that to what we're getting out compared to what's coming in, so we can know what's coming in. So if we say 200 liters per hour is what's coming out of the membrane, so that's the permeate, well, we divide that by 0.95 to get our what's fed to the membrane, and that's 210.5 liters per hour. So the difference between those two is going to give us the flow in the retentate, so 10.5 liters per hour in the retentate, which is approximately 5%. And so given all of that, we see we can solve then for our mass balance here to solve for the concentration in the retentate. Now that we have the concentration in the permeate, given the concentration in the feed, got all these flow rates, it just becomes a matter of rearranging those and solving. So we get 515.8 milligrams per liter of particles in the retentate. So as we see, it's highly concentrated. That's kind of the point. And so that's part C. And then part D, we are given some flux, and we're asked to calculate the total membrane area. This one's pretty simple. We have our flux equation. We're not given any information about pressure or resistance in this problem, so that didn't really apply. So we have 25 liters per square meter per hour. Total membrane area is what we're asked for, so we rearrange to say area is Q over J. And that becomes 200 liters per hour divided by 25 liters per square meter per hour. So 200 divided by 25 should be 8. And that's 8 square meters then. All right. Any questions, issues? Yeah.
How much would it have mattered if we determined the 200 liters per hour as and then because when I
Yeah.
that's
Yeah. So there's a very good question. Let me answer this because this is relevant on exams, right? So if you had interpreted that 200 liters per hour as feed, and the wording here is admittedly vague, what I would do, let's say on an exam, if you come to me and ask me and I can clarify, I might post that as a clarification for everybody. But if I felt like you really should have had it one way, this would be like a 10% type of like a 1 point off kind of a situation where I'd see. This one is vague, so I'm not saying that you should one way or the other this way. I had just said at the beginning that probably do one way. All right, so I'll see you guys on Thursday.